acids and bases. Yesterday we discussed about Bronsted theory. Bronsted theory explains the behavior of acids and bases in terms of a proton. In that, according to that theory, so many compounds were not comes under the acids and bases because it was restricted acids and bases which can donate a proton or which can accept a proton. But here in this theory, other subspecies which are actually acids and bases can be explained as acids and bases and why they were acids and bases. According to Lewis theory, any species which can donate a pair of electrons to other species to form a covalent coordinate bond is considered as a base, and the species which can accept a pair of electrons to form covalent coordinate bond is considered as an acid. That means, according to this theory, electron pair donor is a base and electron pair acceptor is an acid. So the acid-base reaction involves the formation of covalent coordinate bond. That means the neutralization reaction in this theory was explained in terms of covalent coordinate bond formation. Acid. Acid is a species which can accept a pair of electron from other species to form covalent coordinate bond. Base is a species which can donate a pair of electron to other species to form covalent coordinate bond. It means electron pair donor is a base and electron pair acceptor is an acid. For example, if we take NH3, ammonia. This NH3 central atom is nitrogen. In nitrogen we are having a pair of electrons. Valency shell of nitrogen we are having a pair of electrons. Here we have a proton which will have an empty orbital. Now when these two are in contact with each other, so nitrogen can donate a pair of electrons. This is NH3. One pair of electron is present here. And hydrogen is having an empty orbital. And these two will form a covalent coordinate bond. And this covalent coordinate bond will be denoted with this sign. This arrow showing from donor to acceptor. From donor to acceptor. Now the thing is, what type of species can accept a proton? That means classification of acids according to Lewis theory. So according to Lewis theory, electron pair acceptor is an acid. So when a species can accept a pair of electrons, when a pair of electrons can be accepted by a species only if it has an empty orbital. The existence of empty orbital in many ways. So these acids can be classified in the following ways. Number one, molecules having empty orbital in their valency shell. So those molecules which are having empty orbital in the valency shell of their central atom are considered as acids according to Lewis theory. According to Lewis theory, those molecules which are having empty orbital in the valency shell of their central atom can be considered as acids. That means electron deficient compounds are acids according to Lewis theory. What are electron deficient compounds? Electron deficient compounds are the compounds in which without octet configuration, if they are stable, those substances can act as Lewis acids. We know that according to octet rule, a molecule is stable when its central atom and surrounding atoms have octet configuration. But there are certain molecules in which without octet also they are stable. For example, boron chloride and boron fluoride. That means all the family, that boron aluminum family will have this less than octet configurations. Now let us observe how BF3 is forming. BF3. In BF3, central atom is boron. Boron atomic number is 5. So its electronic configuration is 1s2, 2s2, 2p1. This is the valency shell of boron. In boron valency shell, we have 2 electrons in 2s orbital and 1 electron in 2p orbital. 2 electrons in 2s orbital and 1 electron in 2p orbital. And here this p orbital is empty. Sorry, 2p1. 2p orbitals are empty. On excited state, this 2s electron will enter into the empty p orbital because the energy of 2s and 2p is almost equal in boron. Energy difference is very less. When chlorine or fluorine approach to it, this s electron will excited and enter into the 2p orbital. Then electronic configuration against to the rules of electronic configuration, the electronic configuration will become as 2s1, 2p2. Now if you observe, one half-filled s orbital and two half-filled p orbitals are present. Now boron is in a position to form 3 covalent bonds. It will undergone to sp2 hybridization. Because of that, 3 sp2 hybrid orbitals are formed. 3 sp2 hybrid orbitals formed, which are in planar trigonal shape, and each orbital accommodates 1 electron and in a position to form bonds. Now here one empty p orbital is there. This empty p orbital will lies perpendicular to the plane of this orbital. It will have 2 electrons. Empty orbital, it can take 2 electrons. Let us represent this empty orbital. Actually, it is 90 degrees perpendicular, but just I am representing like this, empty orbital. Now, boron when forms, each fluorine atom, if you observe, fluorine atomic number is 9. So its electronic configuration is 1s2, 2s2, 2p, 5. So in the valency shell of fluorine, we have 2 electrons in 2s orbital, and in 2p orbital we have 1, 2, 3, 4, 5. That means 1 half-filled p orbital is present in fluorine. Now this half-filled p orbital of fluorine overlaps with half-filled sp2 hybrid orbital of boron to form b dash f sigma bonds. Such 3 bonds are formed. Now here, this is the molecule which contains an empty orbital in the valency shell. So such molecules which are having empty orbitals in their valency shell will act as Lewis acids. So now we are studying about the types of Lewis acids. The first type is the molecules which are having empty orbital in the valency shell of the central atom. Just now we discussed about boron trifluoride. In a similar manner, we have boron trichloride, BCl3, BF3. Examples are BF3, BCl3, AlCl3, FeCl3, etc. are under this category. They can be considered as Lewis acids because in their central atom we have an empty orbital. This is first category, Lewis acids. Now, second category Lewis acids are all positive ions. All positive ions, including d block elements, are considered as empty orbital. All positive ions and d block elements, all d block elements are considered as Lewis acids, because any positive ion is obtained. When the positive ion is obtained, if it loses an electron, 1 or 2 electrons from its valency shell, then the atom will convert it into a positive ion. So when an atom loses electrons, means the electron present in the valency shell is vacated, is removed. When electrons are removed, automatically it will have an empty orbital. So all positive ions will have empty orbital. They are in a position to accept electron pair from other species. Similarly, all d block elements have empty d orbitals in their valency shell. So all d block elements and their ions are considered as Lewis acids because they have empty orbitals in their valency shell. And third category is the molecules having double bonds other than C double bond C. The molecules which are having double bonds other than C double bond C are considered as Lewis acids. These are the three categories of Lewis acids. Molecules containing double bonds other than carbon-carbon double bond. For example, ethylene CH2 double bond CH2. Sorry, other than carbon-carbon double bond. That means CO2, SO2, SO3 or NO2, N2O, etc. Oxides of nitrogen, oxides of non-metals, all will have double bonds other than carbon-carbon double bond. So all these species is considered as Lewis acids, because by shifting of this double bond to one of the bonded species, one atom will contain, suppose for example, as electronegativity of oxygen is more than carbon, this bond will shift. Because of the shifting of that pi bond, you will have an empty orbital will arise on central atom, so that they can accept an electron pair from other species to form a covalent coordinate bond. So all species, all the molecules which are having double bonds other than carbon-carbon double bonds are said to be Lewis acids. Now, here Lewis theory explains the behavior of acids and bases in terms of electron pair donation or electron pair acceptance. According to Lewis theory, the species which can accept a pair of electron from other species is considered as an acid, and the species which can donate a pair of electrons is considered as Lewis base. Now, in present condition, we are going to discuss about Lewis acids. These Lewis acids are broadly classified into three types. They are, first category, the molecules which are having empty orbitals in the valency shell of their central atom. Those molecules which are having empty orbital in their valency shell of their central atom are considered as Lewis acid. That means electron deficient compounds. All electron deficient compounds are Lewis acids. Examples: BCl3, BF3, AlCl3, FeCl3, etc. are Lewis acids. All these species can take a lone pair of electrons from other species. Lone pair of electron means non-bonding pair of electron in an ion or a molecule is considered as lone pair. Now, second category of Lewis acids is all positive ions including D block elements are considered as Lewis acids, because positive ion is obtained when a species or when an atom loses electron. When electron was vacated from that orbital, then positive ion is formed. So all positive ions obviously having empty orbital, and they are in a position to accept electron pair from other species. So they are considered as Lewis acids. And third category of Lewis acids is the species which are having multiple bonds other than carbon-carbon bonds. Because in these multiple bonds, one atom will be more electronegative than the central atom. In such cases, bond shifting will take place. An empty orbital will arise on the central atom so that it can form or accept a pair of electrons from other species. Such species are said to be Lewis acids. Example, CO2, SO2, SO3, and all oxides of non-metals will have such type of double bonds, and they are said to be Lewis acids. Now, let us discuss about Lewis bases. According to Lewis theory, base is a species which can donate a pair of electron to other species and form covalent coordinate bond. So bases are the species which can act as electron pair donor. A species, whether it may be an ion or a molecule, when it is capacity to donate a pair of electrons. So such species is considered as Lewis bases. Now here also, just like acids, we can classify the Lewis bases also in three types. One is the molecules which are having non-bonding pair of electrons in the valency shell of their central atom are considered as Lewis bases. Lewis bases are the species which will have a lone pair of electron in the valency shell of their central atom. What is the meaning? How do you know such species? Let us observe a species, important species, that is NH3. In NH3, central atom is nitrogen. Nitrogen atomic number is 7. So its electronic configuration is 1s2, 2s2, 2p3. That means this is valency shell of nitrogen. We have 2s2, 2p3. In 2s orbital, we have 2 electrons, and in 2p orbital, we have 3 electrons. So that here in the valency shell of nitrogen, we have 3 half-filled p orbitals and 1 completely filled 2s orbital. In the formation of, or during the formation of a molecule, it will undergone to sp3 hybridization. When it undergone to sp3 hybridization, it forms 4 hybrid orbitals which are tetrahedral in shape. Now when 5 valency electrons of nitrogen, when distributed in these 4 hybrid orbitals, it will be like this. 3 hybrid orbitals are filled with 1 electron each, and 1 hybrid orbital with 2 electrons. So now in the formation of bonding, only half-filled hybrid orbitals will involve. So the half-filled sp3 hybrid orbital of nitrogen will overlap with half-filled 1s orbital of hydrogen to form NH sigma bond. Such 3 sigma bonds are formed in nitrogen and in between nitrogen and hydrogen, and the molecule is in pyramid shape like this. So in this molecule, you will have one p orbital with 2 electrons. Sorry, one sp3 hybrid orbital with 2 electrons. Now, in NH3 molecule, the central atom nitrogen is having 4 pairs of electrons, octet configuration. In this, out of these 4 pairs, 3 pairs are involved in bonding and other pair is not involved in bonding. So those electrons are electron pairs which are present in the valency shell of a central atom but not involved in bonding are said to be non-bonding pair of electrons or lone pair of electrons. Such molecules which are having a non-bonding pair of electrons can donate that pair to form the bond, because in nitrogen's valency shell we have 4 pairs. 3 pairs are already involved in bonding, 4th pair is not involved, so naturally that pair is also have intention to form the bond, provided if any species is having an empty orbital. So now it is ready to donate, because you can donate anything if there is other person is ready to take it, then only donation will happen. Now I am certain amount of money or certain books are there with me, I want to donate. When this donation process is completed, if any needy person is there to take, then only I can donate, or else whatever that I want to donate, it will be with me. I cannot donate unless other person is there to accept. Here also, in the valency shell of nitrogen of NH3 molecule, one pair of electron is there. Now NH3 molecule is trying to donate it, provided if other species is there to take. So which species can take this? The species which is needy in it. When a species is needy in it, if it has an empty orbital. So previously we have already discussed which species can have empty orbitals. One is the molecules which are having empty orbital in the valency shell, that is electron deficient compounds. So second category is all positive ions. Third category is compounds containing double bonds other than carbon-carbon double bond. So such species when approach NH3 or come nearer to NH3, then there will be a possibility for the donation of lone pair of electrons, so that this NH3 is considered as an acid base and other species will be considered as an acid. Now, like Lewis acids, now we can also classify the bases into 3 types. That is, first type, so molecules which are having lone pair of electrons in the valency shell of their central atom can be considered as Lewis bases. Now, second category of Lewis bases are all negative ions. All negative ions. All negative ions means any species which is having negative charge on it is considered as a negative ion. So Cl minus, NO3 minus, HSO4 minus, OH minus, CH3COO minus, etc. are considered as Lewis bases. In other terms, if you recollect the thing which you have explained in Bronsted theory, all these species are conjugate bases of Lewis acid, Bronsted acids. But for example, if you add H plus ion to these species, you will get one acid. So the conjugate bases of Bronsted acids, are considered as Lewis bases. That means all Bronsted bases are Lewis bases. All Bronsted bases are Lewis bases because they have negative charge. And that negative charge means lone pair of electron is present, so that they can donate that pair of electrons to other species. That's why they can be considered as Lewis bases. All negative species, all conjugate bases of Bronsted bases are considered as Lewis bases. And third category is molecules having double bonds or triple bonds between 2 carbon atoms. double bonds or triple bonds between two carbon atoms. So such compounds which are having carbon-carbon double bond, if any cation is approaches here, this pair, because each bond is associated with or contained with a pair of electrons. If any cation reaches to it, it can accept that pair and forms covalent coordinate bond. So the species which are having carbon-carbon double bonds are considered as Lewis bases. So we have three types of Lewis bases and three types of Lewis acids. So in any acid-base theory, it is more essential to explain neutralization reaction and strength of acids and bases. So here, according to this theory, neutralization is a process. Neutralization is nothing but a reaction between acid and a base. So during neutralization reaction, acidic loses its acidic character and base loses its basic character, and a neutral compound will be formed, which is neither be an acid nor be a base. That reaction is said to be neutralization. So in neutralization reactions, according to Lewis theory, covalent coordinate bond formation between the two species is said to be neutralization. Covalent coordinate bond formation is considered as neutralization according to Lewis theory. So according to Lewis theory, if base donate a pair of electron and acid accept the pair of electron, and both will combine to form a covalent coordinate bond, that reaction is considered as neutralization reaction. For example, if you take reaction between NH3 and BF3, we have already observed the structure of NH3. It has a lone pair of electron in the valence shell of nitrogen molecule. In the NH3 molecule, valence shell of nitrogen will have a non-bonding pair of electrons. And we have already observed the structure of boron, BF3, where boron valence shell is having one empty orbital. If such species are in contact with each other, electron pair will be donated by nitrogen and boron will take that electron pair to form a covalent coordinate bond between nitrogen and boron. This covalent coordinate bond is denoted with this arrow like thing. Here this arrow indicates from donor to acceptor. Now normal covalent bonds are present here, BF3. So that reaction is considered to be a neutralization reaction. Similarly, we can observe the formation of NH4 plus. In H plus ion, we have an empty orbital. In NH3, we have a lone pair of electrons in the valence shell of nitrogen. Now, NH4 plus here, nitrogen forms 4 bonds. Octet is completed here. So 3 bonds, NH bonds are covalent bonds. One NH bond is covalent coordinate bond. So sometimes in the competitive examinations, they will ask us how many types of bonds are present in NH4Cl. NH4 is a positive ion. You will have one unit positive charge. Cl minus is a negative ion. So here in the NH4 molecule, one positive charge will exist because this is H plus ion. The positive charge remains after the formation of covalent coordinate bond also. So here in NH4Cl, we have 3 NH covalent bonds, 1 NH covalent coordinate bond. In between NH4 plus and Cl minus, we will have an ionic bond. So in NH4Cl molecule, we cannot consider it a molecule because it is an ionic compound. We can find 3 types of bonds: covalent bond, ionic bond and covalent coordinate bond. All three types of bonds are present in NH4Cl. And this type of covalent bond can also be formed in H3O plus ion. In H plus ion, we have an empty orbital. In H2O, we have two pairs of electrons in oxygen. Now, this pair can be donated to H plus ion to form H3O plus ion. Actually, H3O plus is in pyramid shape, just like nitrogen, NH3. It is in pyramid shape because it has one more lone pair of electrons with positive charge. It is in pyramid shape. So formation of H3O plus ion is another example for neutralization reaction between H plus ion and H2O. So this is regarding neutralization. What about strength of acids and bases? Brownstein theory explains strength of acids and bases. In 10th class, we have studied about the Arrhenius theory. It can also give the reasons and explain beautifully regarding the neutralization and heat of neutralization and strength of acids and bases. But here in the Lewis theory, the strength of acids and bases were not explained, because here acid-base reactions are explained in terms of electron pair donation and electron pair acceptance. The process itself is a very slow process. The donation and acceptance of electron pair from one species by other species to form a covalent bond formation is a very slow process. So in such process, you cannot claim which can give more effectively or more like that. If donate a proton or acceptance a proton is a fast reaction. So those species which can give fastly, they can consider a strong acid, which can give it slowly, they can consider as a weak acids. Similarly, those species which can accept readily the protons are considered as strong bases, which can accept the protons in a delay manner are considered as a weak bases. But such case is not there. As a whole, it is a slow process. So we cannot discriminate strength of acids and bases, or strong acids and strong bases. So according to this theory, the strength of acids and bases were not explained. This is one of the defect of this theory. Another important defect of this theory is it is comparing. Neutralization reaction is a very fast reaction. Within fraction of second, instantaneously, the reaction will be completed. But here, acid-base reaction is explaining in terms of very slow process, that is formation of covalent coordinate bond, which is not proper at all. So these are the main defects of this theory. Ionic product of water. Ionic product of water. Ion product, that means product of the concentrations of the ions that were present in water is said to be ionic product of water. Water is a weak electrolyte, H2O. Water means H2O. It is a weak electrolyte, so it slightly ionizes to give H plus and OH minus ions. The ionization of water is a reversible reaction. So in equilibria, we have studied these reversible reactions in detail. So here, the ionization of water is very less extent. To a small extent, water will ionize, less than 1%. So whatever it may be, you will have H plus ions and OH minus ions in water. Now, If we apply or if you write an equilibrium constant for this reaction, because any reversible reaction at one stage it will reaches equilibrium state, because it's a liquid, there is no need of having closed vessel or open vessel, because only for gases only equilibrium will attain when the reaction is carried out in a closed container. But for liquids it is not so. So equilibrium will establish even in the open vessel, because they are liquids. This is also exist as aqueous ions, AQ ions, OH minus AQ. That means associated with water molecules. So it is in equilibrium. If we write an equilibrium constant for this reaction, the equilibrium constant K is equal to concentration of H plus ions into concentration of OH minus ions by concentration of H2O. Because the square brackets, if anything was represented in square brackets, we considered it as its molar concentration. Molar concentration means number of moles present in 1 unit volume is said to be, or 1 liter is said to be molar concentration. So irrespective of the number of ions, the H plus ions that present in 1 liter is considered as its molar. Le-Chatelier's principle. According to Le-Chatelier principle, when the reaction is in equilibria, if we make any changes in the influencing factors like concentration, temperature and pressure, the system will adjust itself to minimize the change. When a reaction is in equilibria, if we make any changes in concentration, temperature and pressures, the system will adjust itself to minimize the change. Now let us explain the effect of concentration, temperature and pressures in the preparation of sulfur trioxide by contact process. Because in the preparation of sulfuric acid, the main reaction is preparation of sulfur trioxide. If sulfur trioxide is prepared, if we dissolve in water, we will get sulfuric acid. So in contact process, sulfur dioxide gas is allowed to react with oxygen to give sulfur trioxide. This is a reversible reaction. It takes place when these two gases are in contact with catalyst. That's why this reaction is said to be contact process. Preparation of SO3 by contact process. Now here in this reaction, it is exothermic reaction. In forward reaction, 44.1 kilocalories of energy will be released. That means forward reaction is exothermic automatically, and backward reaction is endothermic. Now they ask us to explain effect of concentration, temperature, pressure and catalyst in the preparation of sulfur trioxide by this contact process. Now let us discuss one by one. Effect of concentration. Concentration means concentration of sulfur dioxide, concentration of oxygen, concentration of sulfur trioxide, because the reaction is carried out in a closed container. Now, if the reaction is in equilibria, equilibria means rate of forward reaction will be equal to rate of backward reaction. When the reaction is in equilibria, if we increase the concentrations of SO2 and O2, that is reactants. If reactants concentration is increased, according to Le-Chatelier principle, if we make any change, the system will adjust itself to minimize the change or bring it to the former one. So now the reaction is in equilibria. After equilibria, what we have done? We increase the concentration of SO2 and O2. Now what the system has to do? System has to decrease or bring it to normalcy. So to make this or to decrease the concentration of SO2 and O2, what has to be done? These two must take part into the chemical reaction so that their concentration will decrease. If they take part into the concentration, If they take part into the reaction, what will happen? Concentration of SO3 will gradually increases. That means if we increase the concentration of SO2 and O2, according to Le-Chatelier principle, the system will adjust itself to decrease the concentration. That means it favors the forward reaction to produce SO3. For example, if SO3 concentration is increased, if you increase the concentration of SO3, according to Le-Chatelier principle, the change that you have done should be nullified or neutralized or bring to normalcy. So this can be done only when SO3 decomposes to give SO2 and O2. So increase of SO2 and O2 concentrations favors forward reaction, and increase of SO3 concentration favors backward reaction. Here our problem is to produce more SO3. So to produce more SO3, backward reaction should be stopped, forward reaction should be increased. So for that purpose, what we have to do, time to time, the SO3 prepared in the container should be removed or should be dissolved in water, so that the concentration of gases will be decreased. And time to time, if we increase the concentration of SO2 and O2 in 2:1 ratio, more SO3 is produced. Vice versa, if you decrease the concentration of SO3, if you increase the concentration of SO3, it favors backward reaction. So, with respect of concentrations, to produce more SO3, time to time, SO3, SO2 and O2, that is sulfur dioxide and oxygen concentration should increase in 2:1 ratio, and SO3 must be decreased or removed from the container time to time. This is the effect of concentration. Now, effect of temperature. Effect of temperature means in this equilibrium reaction, forward reaction is exothermic, backward reaction is endothermic. Forward reaction is exothermic, that is heat is generated in the forward reaction. Heat is absorbed in the backward reaction. Suppose when the reaction is in equilibrium, if we increase temperature, what happens? The change that we have done is increasing of temperature. According to Le-Chatelier principle, what the system will do? The system will minimize the change or nullify the change. That means if you increase the temperature, the system will decrease it. So decrease of temperature takes place when the heat is absorbed. That means increasing of temperature favors backward reaction. If your temperature is increased, system favors the backward reaction. If you decrease the temperature, system favors the forward reaction. That means low temperatures are favorable conditions for forward reaction. So in the preparation of SO3, low temperatures are favorable conditions. In the preparation of SO3, low temperatures are favorable conditions. But at very low temperatures, the rate of the reactions are very less. That's why in optimum temperatures, 550 to 750 degrees centigrade is maintained. Next, pressure. Here, in this reaction, 2 volumes of sulfur dioxide react with 1 volume of O2 to give 2 volumes of sulfur trioxide. That means 3 volumes of reactants are producing 2 volumes of products. The number of volumes, that means in same conditions of temperatures and pressures, the volumes are in the ratio of the number of moles. That means 3 moles of reactants are giving 2 moles of products. 3 moles of reactants are giving 2 moles of products. So here, if you increase the pressure, effect of pressure will be on the volume. Volume should decrease. That means if you, at equilibrium state, when the reaction is in equilibrium, if you increase the pressure, volume should decrease. Decrease of volume will take place only when lesser number of products are formed. That means increase of pressure here favors the forward reaction. But very high pressures, the reactors may spoil because of the more acidic character of SO3. Just very low pressures, 1 to 2 atmospheres is maintained in the preparation of SO3 by Haber's, this contact process. Next, fourth one is catalyst. Catalyst. Here, platinized asbestos will act as a catalyst. Of course, after attaining equilibrium, catalyst may not have any role, but to attain equilibrium at an earliest, catalyst will helps us. So in the preparation of SO3 by contact process, the thing is constant with respect of concentrations. With respect of concentrations, SO2 and O2 are increased time to time in 2:1 ratio, and SO3 should decrease. SO3 concentration is decreased by removing SO3 from the container time to time. This is with respect of concentration. Next, low temperatures favors forward reaction. Low temperatures favors more production of SO3, but very low temperatures, the system will not, the rate of the reactions are very slow. So an optimum temperature 450 to 550 degrees centigrade temperatures will be maintained. Next, pressure, high pressures favors forward reaction, but because of acidic nature of SO3, only 1 to 2 atmospheres pressure will be maintained. Platinized asbestos will be used as a catalyst. These are the 4 optimum conditions that we have to take in the preparation of SO3 by contact process.